right in there.
Yeah. All right. Well, I'm extremely sorry to everyone. I had a little emergency to deal with at home. All right. So let's see. So last time Robin told you about computability, about so about reducibility, concept of a Turing degree, which is like a set of all of the languages that are interreducible to one another. Let's see, and recognizable languages, ones for which there's a Turing machine that will halt and accept if the answer is yes, but if the answer is no, if your string is not in the language, then it might run forever. So problems, that are Turing equivalent to the halting problem. Okay, and there are some, very non-obvious examples of such problems. The solvability. I give you an equation and I ask you, does it have an integer solution or not? Right? People. This was another one of Hilbert's problems, right? But it was shown. In 1970, finally, that for any Turing machine, for any computer program, really, it is possible to construct an equation that has an integer solution if and only if the Turing machine halts. Okay, which is a very cool fact. By the way, we started the whole. Discussion of computability by talking about the Hilbert's-Entscheidungs problem, right? Which is just, is there a sort of general purpose way to automate mathematics? Is there a machine where you could feed it any mathematical statement and it will just tell you whether it's true or false? Okay, so what's the answer that we get from this is no, because I give you an equation. Does it have an integer solution or not? That's certainly, that sounds like a mathematical question. Okay, but that already can be at least as hard as the halting problem. Okay. Okay. And then. Robin also told you about, that the halting problem is by no means the hardest problem, okay, that you can have. In fact, given any language whatsoever, it is possible to define an even harder language, right? And what do we mean by even harder? If something's already uncomputable, isn't that hard enough, right? But we mean, that even if you had, so given any language L, you can define, another language where even if you had an oracle for L, the new language would still be uncomputable, okay? And and how do we define that? Well, we could just consider the halting problem for Turing machines that have oracles for L. Okay, so you can just sort of repeat everything, just another level up. Okay, and exactly the same argument that we already saw that told us why the halting problem is undecidable by a normal Turing machine will also tell you why the halting problem for Turing machines with L oracles is undecidable by a Turing machine with an L oracle. Okay, so so no matter how powerful you are, you still can't solve your own halting problem. Okay, it's one thing you can't do. All right, so this concept of an oracle, which we use in reducing one problem to another one, or sort of, seeing like what is the structure of the different problems, how do they relate to each other, and this is a concept that will show up again and again in the course. Okay, so. So the Turing degrees, that we've seen are, there's the Turing degree of all of the computable languages, okay, and that's at the very bottom. Computability theorists actually call it 0, okay, and then there's the Turing degree of everything that's equivalent to the halting problem, okay, which includes, a lot of interesting mathematical questions, solvability of equations, this matrix mortality problem, Robin also showed you, okay, and then you can keep going up higher and higher, the super halt degree, super duper halt, super duper pooper halt, whatever. So, now, one of the I'm not sure if Robin told you this. One of the first questions, like a mathematician, might ask, looking at this picture, is, well, great. So, is there anything in between this and this? Okay. Just like when we saw the infinity of the integers and then the even greater infinity of the real numbers, we ask, okay, is there anything in between? And we saw in that case, that was a big open problem called the continuum hypothesis. And the answer turned out to be, well, in some sense, there is no answer. Okay, either answer you want is, equally consistent with the axioms of set theory. Okay, in this, but in the case of computable versus the halting problem, so the question of whether there's any Turing degree in between the two was called Post's problem. Emil Post was actually a high school teacher in New York who came up with computability theory basically independently of Turing and Church. This is true, okay? And so and he first raised this question and was unsolved until the 50s, and then finally Queenie and Post, he and Steve Queenie solved it, and then there was so Queenie and Post showed that yes, there are such Turing degrees in between. And then Friedberg and Muchnick showed that you can even get recognizable languages that are in between. Okay, so what exactly do we mean by in between, right? We mean a language L, which is Turing reducible to the halting problem, right? Which is not computable. So we could phrase that by saying that L is not Turing reducible to 0. Okay, that's just another way of saying that it's not computable. Okay, and what would be the third requirement? Yeah, huh? Excuse me? Okay. Well, we want that the halting problem is not Turing reducible to it. Right? So it's, so it's not just so it's genuinely intermediate. Okay, you can get that via some, but it's via a very complicated construction where you basically define the language stage by stage by like killing out every possible Turing machine that could compute it. It's a diagonalization, as we call it, killing out every possible reduction that could reduce the halting machine to it. And so this is not a problem that you're likely to encounter in practice, okay? And since then, computability theorists have found that there are actually infinitely many Turing degrees in between computable and the halting problem, and there's a lattice. There are like multiple ones that are incomparable to each other. So meaning like there's A and B, where if you had an oracle for A, it still doesn't let you solve B, but if you had an oracle for B, it still doesn't let you solve A. You can have that, right? And you can have this structure that's been sort of studied in more detail than you can possibly imagine, okay? And yes, there are also Turing degrees that are not Turing reducible to the halting problem at all, right? Or to any of these problems up here that are just off to the side somewhere. And in some sense, most Turing degrees are like that because there's an uncountable infinity of Turing degrees, right? Most of them are just like, if you just defined a language completely at random by just flipping a coin infinity times, that would probably just give you, and then you took the set of all the languages that are Turing equivalent to that language, that would be another Turing degree. Okay. So. Okay, so what's on the agenda for today? So the first thing I want to do is tell you about the technique of dovetailing, which is a very useful technique in computability. For example, for showing things are equivalent to the halting problem, and then we're going to talk about Gödel's incompleteness theorem. Okay. All right. So all right. So you saw on Tuesday that there are you can give reductions to show other problems are equivalent are Turing equivalent to the halting problem. Okay, like for example, the halting problem for Turing machines that take input is equivalent to the halting problem for Turing machines that don't take input. That's a very simple example, okay? Or, the halting problem for two-tape Turing machines is equivalent to the halting problem for one-tape Turing machines, right? You can reduce, if you had an oracle for one, you could use it to solve the other. Okay, so here, let me give you a slightly less obvious example. Okay, so let's consider the language that consists of all descriptions of Turing machines for which there is an input that causes them to halt. Okay? So all the Turing machines that halt on some input. So now, we would like to understand, this language. It shouldn't surprise us much if it's, that this language is uncomputable. So I claim that the halting problem is reducible to L. How do we do that? Let's say that I've got a Turing machine and I just want to know, all I want to know is just does it halt on a blank input? Okay, but now I've got an oracle for deciding this L. How do I reduce the one to the other? Anyone? Yeah.
You can construct a Turing machine that runs and like whatever the input of your would have been. And no matter what input, it just does that.
Perfect. Yeah, you can just design a, so given, a Turing machine M, let's say, for which you want to know whether it halts or not on a blank input. So now just modify it to get a new Turing machine, say M prime, that when you run it, it just deletes its input. It just, wipes the board clean, okay? And then starts running M, doing whatever M would do from that point forward. All right, easy. All right, so now, a little less obvious is the other direction. So if we had an oracle for the ordinary halting problem, then could we decide L? Okay, so the question here is, you've got you've got this program. You want to know whether there's any input that causes it to halt, right? But now, can you design, say, just a single Turing machine, just like with no input? Which halts if and only if there exists an input that causes M to halt. Can anyone think of how to do that? I mean, yeah.
I guess you could make it run through, like you could make it like go through every single possible input, and then halt when one of them accepts or rejects.
Yeah, in some sense, yeah, that's on the right track. We got to be a little careful about how we do it, right? So the issue is, what we'd like to say is just like try the first input, see if it runs wherever it halts. Try the second input, try the third input, and so forth, and then see if we ever find an input where it halts, and if we do, then halt. Okay. The problem is that just for each individual input, just deciding whether it halts already requires solving the halting problem, right? Just for each individual stage. So then, what we're really asking for, if we want to just do this over all inputs, is not to solve the halting problem for an ordinary Turing machine, but to solve the halting problem for a Turing machine with a halt oracle, right? You see that there's like there's like a second layer in here, right? And we've seen that the halting problem for Turing machines with halt oracles is actually harder than the halting problem. That's the super halt problem. Okay, so if we just do it like that, it's not going to work. So here's a picture to have in mind. So imagine that we just listed all the possible inputs. Okay, and here's like the amount of time that they run for. Like the amount of time that M runs for if you feed these inputs to M. Okay, and so for a whole bunch of them, M runs forever. Okay. At least for a really, really long time. It runs forever. Okay, but then there's one input, let's say somewhere, where it halts. Okay. So we can't just if we try to like simulate for the earlier inputs until they halt, right? We're just going to get stuck there forever, and we're never even going to find out that there's this later input where the thing does halt. Okay, so the general way to deal with this sort of problem was a useful technique called dovetailing. It's almost too obvious to need a name. Okay, but I'll show you. It has there's a nice picture to remember. Okay, and the basic idea. Is this, that you first simulate, running M on the first input for one step. Okay? Well, it hasn't halted. okay? Then, you run M on the first 2 inputs for 2 steps each. Okay, then you run it on the first 3 inputs for 3 steps each, right? And so on. Okay, so this, this is what it's, some people apparently thought that this looks like a dovetail. Okay, so you keep going like this until up, lo and behold, after a finite amount of time, you found this thing. Okay, it's actually kind of similar to how one shows that the set of rational numbers is countable. Right? Okay. All right, so now let me do a still more interesting example. So all right, so the conclusion is that indeed this language is Turing equivalent to the halting problem. Okay. Okay, so let's consider the language that consists of all descriptions of Turing machines for which, they're, let's say, Turing machines with an oracle, so that can read an oracle. But, one way to think of an oracle is just as an infinitely long input. Okay, it's an input that never ends, right? Because it has a bit for every possible question that you could ask it. And so now we consider the language consisting of all programs for which there is some oracle that causes them to run forever. Okay, that that sounds like a weird thing to wrap your head around, right? But all right, so. Once again, I claim that this language is uncomputable. Can anyone tell me why? If we had an oracle for this language, how could we solve the halting problem? Well, the ordinary halting problem, I mean. Yeah?
You could accept one machine and you know that it runs forever. Then you just know that whether or not it halts.
Yeah, well, I mean, look, the ordinary halting problem is for Turing machines that don't even access an oracle at all, right? Doesn't say anything about it. So you have some M that never queries an oracle, right? And then, you just, it will, if it never even uses the oracle, then it's going to be in L if it runs forever. So that's already the halting problem. Okay, so all right, so that's easy. So once again, the more interesting direction is, yeah. Yeah, you're right. It is. So it's very convenient for us that we're talking here about Turing reducibility, right? Where if you have an oracle, you can always just get whatever answer it spits out and then just negate it. Saying, right? That's so actually you raise a good point, right? Which is that if we were talking about many-one reducibility, which Robin also defined on Tuesday, then this would not be true. Okay, halt is not many-one reducible to L, right? Because there's no direct mapping from yes instances to yes instances and from no instances to no instances. Right, but there is a mapping from yes instances to no instances and from no instances to yes instances. And that's enough for it to be Turing reducible. Okay, good. So all right, so how about, how on earth, now here's the question. We have a Turing machine that, that queries some oracle, and now I would like to design a new machine, say M prime, with not involving any oracle, okay, which runs forever and say if and only if there exists some oracle that causes M to run forever. Okay, so how could I do that? Mm-hmm. Well, so let's imagine that we've got, our Oracle Turing machine. So you can think of that as just a 2-tape Turing machine. That's got some memory that it, uses to compute with. And it also has this Oracle tape, A. Let me just, think of A as infinite in one direction. So it's just an infinite string. You can think of an Oracle as really just an infinite string of zeros and ones that you have, that you're able to access at any bit that you like. Right? So you can think of the Oracle as just an infinite set of zeros and ones that are, written onto this tape, right? And, containing the infinite wisdom of the Oracle that you can consult as needed, right? And, these are, these are its answers to every possible yes or no question you might want to ask it, listed in lexicographic order. Right, and and when the machine can answer any question by just moving to the appropriate place on the Oracle tape. All right, so the machine starts out in the leftmost position, let's say on the tape, and and as far as the machine is concerned, right, it doesn't know yet what the Oracle is going to say. That's why it needs an Oracle, right? So it could be a 0 and it could be a 1. Right, and the question that interests us, right, is going to be whether there exists any way of setting the zeros and ones on this Oracle tape that causes the machine to run forever. So how are we going to deal with this? Given that now we're constructing a machine that has no Oracle to help it, right? So and we just need our new machine to run forever if and only if there is any way of setting this Oracle tape that causes M to run forever. Okay, so what can we do given that we don't know the first bit? Yeah.
You just try creating different oracles, and if it terminate, then you create this oracle.
Exactly. We can just try them both. We can branch. Okay, so let's say that we're going to sort of create a giant tree of possibilities, okay, where going down the tree, these are the time steps of M, of our original Turing machine, okay? But now anytime M reads a new bit of the Oracle string that it hasn't read before, then we're going to deal with that by just branching on both possibilities, okay? We're going to, see what happens if that bit was 0, and we're going to see what happens if it's 1. Okay, so there are some steps where M is not reading the Oracle at all, or it's only rereading bits that it already read. And so at those steps we just go straight down. Okay, but there can be other steps when M does query a new bit, and then we branch on whether that bit is a 0 or a 1. Okay, and now, it's very, as we simulate this process, it's very, very important that we don't get stuck, in any one branch forever. Does anyone know a technique for searching trees that will let us avoid that problem? BFS, yes, breadth first search. Okay, so we definitely don't want to do DFS. Okay, we're gonna. Because because the D is infinite here, right? Could be infinite, right? So we want to do breadth first search of this tree, right? So we first, kind of like dovetail. We first run the tree 1 level down, then we run the whole tree 2 levels down, 3 levels down, and so forth. We search the tree like that, okay? And now, as we go on, some of these paths may terminate. Well, meaning that at this point the Turing machine halts. Right, so now it's saying that if we had this now is saying that if the first 3 bits on the Oracle tape were 0s, then the machine halts. All right, so now we've learned something. We've learned that if you want M to run forever, then the first 3 bits of the Oracle tape cannot be 0. Okay, but what we want to know is just, is there any way to set the whole tape such that the machine runs forever? So we've got to keep going. We've got to look at the other branches, right? And so other branches may continue for a while. Some of them will eventually stop. Okay, but some of them will keep going down. Okay, and maybe at some point, every branch that we've explored, every single branch is terminated. At that point, what can we say? Yeah, at this point, we can say that there is no oracle that causes M to run forever, right? At this point, we're done. Okay, but now consider the other direction. Suppose that this process never halts. Okay, then what can we conclude? Yeah. Yeah, sure.
Is the input matter to the...
Oh, that's a very good question. So I'm just assuming here that the input is empty. Okay, good. So we'll assume that the input is the all zero string, because I'm just worrying about the oracle here. All right. So suppose that this process continues forever, right? If it continues forever, then that means that the tree must be infinite. Right. Okay. And now there's a slight subtlety which you could miss if you could miss if you blink. Okay. The subtlety is, well, just because the tree is infinite, does that mean that it must have an infinite path? Okay. Well, here's a potential counterexample. Here's an infinite tree, but which has no infinite path. I just have one root vertex, and it's got infinitely many children. Okay? But nevertheless, I claim that this tree, if it's infinite, then it's got to have an infinite path. Well, what's the difference between the trees? Finite degree, yeah. So the general statement that we want here is called Koenig's lemma. And it says that every infinite tree with finite degree, or let's say where every node has only finitely many children, has at least one infinite path. Okay. Can anyone see how we might prove Koenig's lemma? Or why is it true? Yeah.
So if it didn't have an infinite path,
Yeah.
it has a finite degree, then it's a finite tree.
Yeah, that's certainly the intuition, right? So we want to be a little more explicit, right? We'd like, let's say, a procedure for finding the so we should say that this tree has an infinite path. Great. How do we find that infinite path? Yeah.
For every node,
Mm-hmm.
start at the reference
Yep.
node, make it have the maximum number of
Yeah. What?
And so the only way you can grow is down. You have to go.
No, that's exactly the intuition, right? If we want to be a little more formal, we can argue by induction. We can say, look, because the tree is infinite, and because the root, by assumption, has only finitely many, subtrees, only finitely many children, therefore, at least one of these subtrees must itself be infinite. Right? Otherwise, the whole tree would be finite, right? So let's suppose this subtree is infinite. Okay, so then traverse this path. Okay, or go down to this one. All right, now repeat here, right? Because this subtree is infinite, at least one of its subtrees must be infinite, right? So then suppose this one is infinite, then go down here, right? And so you'll always be, maintaining that you've got infinite possibilities to your future, no matter which way you go, so you can continue for infinite time. Okay, so the tree has an infinite path, which in this context means a setting of zeros and ones for the oracle string that causes the Turing machine to run forever. Okay? That must exist if our program that we've constructed doesn't halt. Okay? Good. So, all right, you ready for Gödel's theorem? All right. Good. All right, so Gödel's theorem actually predates the unsolvability of the halting problem by 5 years, and it was a direct inspiration to Turing. Okay, so but we'll see, and the two are closely related to each other. Okay, and we'll see exactly how they're related. But the starting point for Gödel's theorem is not computability, but it's logic, right? And it's sort of paradoxes of logic that go all the way back to the ancient Greeks, right? So you've probably heard this. Some people say that the paradox of the liar is that a Cretan says all Cretans are liars. And then, should you believe them or not? I claim that this is actually not a paradox at all. Okay? Why is there no paradox if a Cretan says that all Cretans are liars? What? Anyone? Yeah, I mean, it could be that. Well, look. I mean, yeah.
He's not saying that they lie all the time, I guess.
Yeah, and well, he's, okay, yeah, there's several ways to do it, right? But let's even suppose that he said all Cretans lie all the time. I claim that there's still no necessary contradiction here. Yeah.
The negation of that
Yeah.
is just that some Cretans lie.
The negation is that some tell the truth, right?
Yeah.
Yeah.
If the truth were that some Cretans lie sometimes,
Yeah.
that would be a lie.
Exactly.
Be one of the some Cretans that lie.
Exactly. That's exactly right. Yeah, it could just be that some Cretans are liars, including that one. Okay, the one who you're talking to, right? And then, and then he is indeed lying, and so there's no problem. Okay, so let's do a better example. Okay, so a pure form of the problem comes in the famous sentence, this sentence is false, right? And if this sentence is false, then that means it's false that it's false, right? But that means that it's true, okay? But if it's true, then it's false, and so forth. So now the question that we face is, why did my writing the sentence on the board not just cause the universe to explode? Why did this not, why does this not create a contradiction in mathematics, right? The challenge here is to explain sort of what is it that sort of rules this sentence out as an illegitimate sentence, right? What are the rules for constructing sentences, or let's say mathematical sentences or something that will prevent us from constructing this sentence? Because if we did construct it, then it's clear that we would have a problem. Okay, so that's sort of the way I want to frame the issue of what it looks like a perfectly grammatical sentence, but there's got to be something wrong with it. So yeah. Yeah, well, okay, so a lot of people, like the first sort of instinct we have is that just the fact that the sentence is self-referential, right? You could say maybe we should just disallow sentences that talk about themselves, right? Because that just seems like a recipe for disaster. Okay, so all right, but very interestingly, and this is going to be important for Gödel's theorem, I claim that doesn't actually solve the problem at all. Okay, let me show you why. All right, actually, this will involve a little digression. Does anyone, probably some of you have seen this before. How do you write a program that when you run it, its output is itself, is its own source code? Yeah.
So there's this language called HQ9+.
All right.
Where if you press Q and run it,
Uh-huh.
print a Q.
All right.
So that's what you do.
All right, good. So in that language, it's quite easy, yeah. So let's say that you're using Java, or you're using, like I've given a programming language. It doesn't have this functionality built into it. I claim you can still do it, right? Tell me in pseudocode how to. Okay. Oh, and by the way, no fair to just write. Have a blank program. Right. There was actually in this international obfuscated C code contest, they had like a competition for years to write the smallest C program that prints its own code. Whose output is itself, and then there's one that's only like 31 characters long. I think you can do like ridiculous stuff in C. Okay, but then one year someone just submitted a blank file. Right, which is technically not a C program, but some C compilers will compile it to a program that does nothing. Okay, so at that point they ended the contest, I think. So all right, but so a non-empty program that prints its own code. So basically what you want to do is, in whatever programming language you want, sort of do the following type of thing. Write a program that basically says, print the following thing twice, the second time with quotes. And then you have in quotes, print the following twice. The second time in quotes. Okay. Everyone see that that's a program that prints itself? Yeah. Okay. It's apparently the name for such a thing is called a quine. Okay. So in recitation tomorrow, you may talk about there's a generalization of this called the recursion theorem, okay, which is a fancy name for a very, very simple observation. It basically says that whenever you are writing a computer program, you can always assume, if you like, that program has access to its own code. Okay, which like it sounds like maybe a paradox if you think about it, right? Because if this program is accessing its own code, right, then what it does depends on its code. But I'm writing the code right now, so it's like what But you can always get around this problem with this sort of trick, right? You have a program that. That sort of, the code of the program, actually contains two copies of the code, and one of them is in quotes. Okay? Yeah?
There should be no period and then there should be a colon.
Yes, thank you. Excellent catch. Okay? It's good. Now it works. Right. Good. All right, awesome. So, but this has some sort of loopy, implications, right? Like, you might think, okay, like let's say there's some artificially intelligent robot, right? And and it's in complete code, right? And so you might think that you could get okay, so now you want to tell it its behavior. Like you want to go to that robot and say since you're a robot, I can predict what you're going to do, right? I know whether you're going to walk, out of the room in a minute. Okay, and the robot says, well, that may be, because it's a smart robot. Okay, it says that may be true, but you better not tell me the prediction, because whatever you tell me, I'll just do the opposite of whatever you say, right? You tell me I'm going to walk out of the room, then I won't. You tell me that I won't, then I will. Okay, but what the recursion theorem says essentially is that you could give the robot your prediction in the form of a program. Okay, you could say, what I predict that you're going to do, is, well, whatever this code, this piece of code that I'm going to hand to you, whatever output it produces when run. Okay, and of course, your act of handing that code to the robot, will change the robot's behavior, right? Because the robot can now look at the code and can do something, having looked at it. But even then, even after the robot has looked at the code that you've handed it, your prediction, as embodied in that code, will still be correct. Okay, it's like the, if you see, I guess, they're like this is the way Greek tragedies work, right? Where the hero, or Oedipus, finds out, the prophecy that he's gonna, kill his father, or whatever it is. I don't really know Greek tragedies, okay? But and then he does everything he can to try to avoid that coming true. But then all his attempts to avoid it just cause it to come true, right? It's kind of like that. Okay, you can, you can give the robot a piece of code that that the robot can take as input, process, do whatever it wants to try to avoid doing what that code says. But after all, it can't. I mean, it could just simulate the code forever. But then that's just an infinite loop, right? If it ever halts, then it will turn out that that running the code would run for a longer, would involve running for a longer time than the robot ran for, and it would have just output the correct prediction of what the robot actually did do when it halted. Okay, so that's the recursion theorem. So, all right. So what does this have to do with this sentence is false? Well, what could we do if we wanted to eliminate the self-referentiality from this sentence? Yeah. Oh yeah, you can always do that. That's true. You can, you could always do like sentence 1 says that sentence 2 is true. Sentence 2 says that sentence 1 is false, right? But all right. But let's say that when we prohibited self-reference, right, our prohibition was actually broader than that. Okay, it actually prohibited any kinds of cycles of sentences talking about each other. Okay. If we're just going to say a sentence is these are privileged objects. They get to talk about other things, but they don't get to talk about themselves. Okay. The problem is that sort of you can't really prevent sentences from talking about sentences that are in quotes. Right, because something that's in quotes is just kind of a string of symbols, right? It could be anything, right? We can always talk about strings of symbols, right? So, all right, you know what? So, you could do something like the following sentence repeated twice, the second time in quotes is false. Quote, the following sentence repeated twice, the second time in quotes is false. All right, so now this sentence is not talking, directly about itself. It's not talking about any other sentence that has sort of, first level status on the page. It's just talking about the string of symbols that that is between quotation marks. They say, that ought to be okay. Okay, and yet implicitly it is talking about itself. Okay, when interpreted, it is saying that it's false. And so then we're back to the problem we had before. Incidentally, I can't resist pointing out that this trick, print the following twice, the second time in quotes, print the following twice, the second time in quotes. This is basically how we work, right? This is basically how DNA works. This is how reproduction works. Okay, we are basically these machines that that carry code, and the DNA code that says make a make a copy of this organism, and then make sure that the copy also contains the code for making a further copy. In other words, it's its own DNA. Okay, you can think of describing an organism by its DNA as like putting the organism in quotes. Okay, so it's a useful principle. All right, so now what this tells us is that the problem with this sentence is false is not actually self-reference, right? It's got to be something else. Okay, and the thing that that sort of logicians zeroed in on in the 20th century as sort of really being the problem is the concept of true and false itself. Okay, so it's not that there aren't things that are true and other things that are false. Okay, but there cannot and this was the conclusion of Alfred Tarski, the indefinability of truth, it's called. And actually, Gödel also observed this on the way to the incompleteness theorem, but he didn't publish it. Tarski liked to call himself the second greatest logician of the 20th century and the greatest sane one. Okay, sort of a mean thing to say about Gödel, I guess. But what Tarski showed is what Tarski said is that there is no there can be no like mathematically definable function f which takes as input a sentence, like of arithmetic, a sentence about, mathematical objects like integers, written out as a string of symbols, and which outputs 1 if s is true and 0 if s is false. Okay, so in other words, there can be no mathematically definable truth predicate. Okay, and why can't there be? Well, precisely because if there was one, then we could construct this sentence, the liar paradox, and then that would be a genuine mathematical contradiction. Right? That would be just like proving 0 equals 1. Okay, so so the conclusion is just that there is no function. Mathematics itself is not able to define a function that just takes an arbitrary mathematical statement and that outputs whether it's true or false. You can believe in the existence of such a function, but that's like a meta-mathematical, commitment. All right, so. All right, but that's just truth. Now the main innovation of Gödel was to concentrate not on truth but on provability. Okay. So So what do we mean by provability? Okay, so to really explain this for real, would require sort of a whole course where we talk about, what is a proof system, right? A proof system is basically just a completely formal system for, talking about math. So it includes a completely formal language for, expressing mathematical statements. Okay. And these languages were invented around, late 19th, early 20th centuries by people like Frege and Russell and Whitehead. Okay, and they say things like, for all x, for all, maybe we can, we would have to define what we meant by integers first, right? But for all the integers, there exists another integer, y, such that some function of fx and y, equals 1, and some other function, of y, equals 0, right? So it's a, so you're allowed to have quantifiers, like universal and existential quantifiers. You're allowed to have logical connectives, like Boolean connectives. Usually there's some equality symbol. There are you can define functions. Okay, so these are this is called the language of first order logic, right? Okay, and then there are proof system also includes inference rules. Inference rule is just a way of taking previous sentences that you believe are true and deriving a new one. Okay, in some completely mechanical way. Okay, so famous example is modus ponens. If you've you've already deduced A and you've deduced that A implies B, then you get B, right? And that's just a matter of turning a crank. It doesn't matter what A means or what B means, right? It's just any two things that have this syntactic form. You deduce this thing. Okay, and then there are other there are other inference rules, like if we knew that f of x equals 1 for every x, then we would also know that f of y is 1. It doesn't matter what y is. Okay, we can so we can sort of, this is called quantifier elimination. All right, and there's the rules of there are other rules for quantifiers, like if it is not true that f of x is 1 for all x, then it is true that there exists an x such that f of x is not 1. Stuff like that, all right? So we have inference rules. And then the third thing that we have is axioms. Okay, so we have certain, statements that we just accept as true to begin with. And so the axioms will depend on, what kind of objects we're talking about. You've seen like the axioms of Euclidean geometry, every 2 points define a unique line and so forth. Okay, the axioms of arithmetic, of what's called piano arithmetic, would say, there exists a 0, there exists a number, say, and every number has, exactly one successor. And if two numbers have the same successor, then they are equal. Pretty believable sounding things, right? The axioms of set theory say things like the empty set exists. You got to start somewhere. For given any given any two, let's see, given any two things, like, given any two sets, there is a union of those, the union of those two sets is also a set. the intersection of those sets is also a set. Then at some point you have to say that there exists an infinite set. Okay, because otherwise you might have just only finite sets, and that would satisfy all your axioms. Oh, you say for every set, the set of all subsets of that set is also a set. Okay, which then lets you, starting from the if any of you have seen the way that set theory works, it's kind of cool. You start with the empty set. You start with complete nothingness. Right, and then people say you can't create a universe out of purely nothing, right? But in set theory, what you do is, all right, we can have the set containing the empty set. That's something new, right? That's a little bit more of something, right? And you can have let's say the set the set that contains the empty set plus the set containing the empty set. And you can keep going like this, and then you can define these to be in one-to-one correspondence with integers, and that gives you numbers. Yeah.
You also just say you can create a set that contains everything except for the empty set.
So you're not allowed to say, I define a set that contains, everything except for such and such. Okay, does anyone know why you can't do that? There's an important reason. Russell's paradox, right? Russell's paradox says, consider, the set of all sets that don't contain themselves. Right? It sounds perfectly reasonable. Okay, but then does it contain itself? Right? Well, it does if it doesn't. Okay, so that's the problem, right? So or another version of it is the barber who shaves everyone who doesn't shave themselves, right? So does that barber shave himself? Okay, so because you can run into paradox, and this was actually Frege wrote a whole book on set theory, spent decades working on it, not noticing this problem, and then Russell sent him a letter saying, well, you can get a paradox, right? If you just allow the set of all sets that have such and such a property, that's trouble. Okay, so what we do in modern, so the modern system for set theory is called Zermelo-Fraenkel set theory, or ZF, right? And the ZF axioms, require, in order for a set to exist, that you've got to sort of build it up in some, starting from the empty set in some way. Right, or they allow you to also start from some, countably infinite set. Okay, and then you could take its power set, so you can get extremely big sets, but every set sort of has to be built up in some way. You can't just say the set of all sets such that blah blah blah. Okay, so anyway, so we have axioms, and okay, so now just some terminology. Okay, and then any statement that we can derive by starting from the axioms and then applying the inference rules any finite number of times is called a theorem. Okay, it's called a theorem of that proof system. Okay, and so now just some terms that we use. A proof system is sound if all of the statements that it can prove are actually true. Okay? If everything provable is true. Okay, now as I said, truth is not itself, mathematically definable. So, you could think of this as just sort of a value judgment, right? This is not a mathematical definition. This is something that we looking in from the outside will with some independent standard of judgment we'll say, okay. But then something that can be defined, in a much more mechanical way is consistency. Okay, consistency just means that the, the system never proves both a statement and its negation, right? So, so at least the system is consistent in what it says, right? Like it doesn't prove that, that 0 equals 1, because presumably it also proves that 0 is not equal to 1, right? So so that would be an inconsistency. Okay, so are these the same thing? I mean, can anyone give? Okay, so is any sound system consistent? Well, presumably so, because the truth should all be consistent with itself, right? But is any consistent system sound? What's an example of something consistent but unsound? Well, if I believe that the moon is made of cheese, but I also believe that the moon tastes really good spread on a cracker, I have all these beliefs about the moon that are all completely crazy, but they're consistent with each other, right? I mean, actually, like you ever talk to, like a conspiracy theorist, you just, it's like an incredible real world example of someone, with like some network of, consistent beliefs that, may be very, very far from being sound, right? So, okay. Okay, then there's this notion of completeness, important for Gödel's theorem. And completeness means that for every statement A, or at least every statement like within the domain of discourse that we care about. So, every sentence that you can form using, every grammatical sentence that you can form using the rules of this formal language, the system proves either A or its negation. Okay? So completeness says that, system, renders a verdict about everything. Okay, and then one final definition, we will call a proof system computable if there's a program, or, in other words, there is a Turing machine that when you run it, lists all the theorems that are provable in the system. Okay, and this computability condition will also be important. Okay, any proof system that you would naturally think of sort of satisfies that condition, because in general you'll be able to satisfy it by just sort of saying start with the axioms, then start deriving consequences from them in every possible way. Do again a breadth first search tree, right, where you just take every possible consequence of these axioms by applying inference rules once, and then every possible consequence by applying the inference rules, to those new statements, another time, and so on and so on, right? And then, in the limit, that will list all of the theorems of your system. Yeah.
Does this mean this program can list down all real numbers?
No. It just means that it can list, all of the theorems that are provable in the system. A theorem, if we're talking about a formal language, right? A theorem is going to be a finite string of characters, right? So in order to even state a theorem, you're going to have to somehow specify which real number you're talking about, right? So so most real numbers, there's no theorem about them just because there's no way to write that real number down in any finite amount of time, right? The very, right, if you're proving a theorem about it, like, it's pi or I or something, it's because you're able to have a short formula that specifies that, what number you mean. All right, so now I can state with this in hand, I can actually state and prove the first incompleteness theorem, okay? And I'll state it in like an informal version. And then we'll see sort of more refined versions of it next week. Okay, so it says, let F be any proof, in this version I'm going to say, let F be any sound and computable proof system, which is sort of powerful enough to express statements about arithmetic. Okay, like sentences about integers. Okay, and I'm being a little bit vague about this, but most natural proof systems like piano arithmetic or Zermelo-Fraenkel set theory, they'll all satisfy this. They'll all fall under this. Okay, then there exist statements of arithmetic, S, which are expressible within the language of F, such that F proves neither the statement nor its negation. Okay, so there are statements that that F, just purely arithmetical statements that F can neither prove nor disprove. Okay. And the famous example